Welcome to this explainer. Today, we're tracing the evolution of AI agents from those early, kind of primitive, amnesiac demos to fully governed, rock-solid enterprise systems. If you've been building or testing AI agents lately, you've probably hit that frustrating wall where your agent just suddenly seems to lose the plot. Well, we're going to look at the exact architectural patterns that separate weekend toy projects from serious production-grade enterprise agents.
So let's jump right into a massive misconception that plagues developers the second they try to scale their applications. We always tend to think that when an agent fails in the real world, it's either because the model just isn't smart enough, or maybe our prompts aren't clever enough. But the reality? It's actually rooted in a fundamental misunderstanding of how these models interact with time and state.
Harrison Chase absolutely nailed the core issue here. LLMs do not inherently remember things. Period. When you call an API like GPT-4 or Claude, it shows up with zero context from your previous request. Any memory you experience in a slick chat interface is literally just an application layer trick, where the front end is rapidly replaying your history. Memory is not a model capability. It is a deliberate, highly intentional infrastructure decision.
Section 1. The silent agent failure. We've got to establish the stakes right out of the gate here, because when a long-running production agent collapses, it's almost always because its state was corrupted or just forgotten entirely. The Anthropic engineering team actually found this exact issue after analyzing dozens of production deployments. Think about it. If an agent handling millions of queries a day loses track of what it just recommended to a user or forgets a user's core preferences, the entire experience just falls apart within minutes. Section 2. The 4 memory tiers. To fix these state failures, we have to treat memory as a multi-tiered system, kind of like human cognition. Every single production agent needs a combination of these 4 tiers. Your in-context memory, that's basically RAM. It's fast, but heavily bounded by the context window and incredibly expensive. Then you have external key-value memory for stable, static facts like user preferences. Next is episodic memory, which acts as an append-only log of events. And finally, semantic vector memory for that fuzzy, similarity-based retrieval across massive knowledge bases. Choosing the wrong tier for your data is, quite frankly, a fatal architectural mistake. Now, a massive mistake developers make is conflating semantic and episodic memory, which leads directly to agents that literally cannot reason about time. You need semantic memory for current truths, but you absolutely need episodic memory for a historical audit trail. Say a user mentions they moved to Berlin. Semantic memory overwrites their old city to Berlin. That's the current truth. But episodic memory logs the exact date they made that statement. Without that episodic log, your agent has zero concept of what happened before the move versus what happened after.
Section 3. 5 memory architecture patterns.
Taking these tiers into a live production environment means you have to balance 2 main axes: accuracy versus latency and governance versus freshness. Moving from pattern 1's highly accurate but agonizingly slow in-process memory all the way up to pattern 5's enterprise context layer, you realize pretty quickly there is no single universally perfect pattern. If you just dumped everything into a massive context window, sure, it's accurate, but you're going to suffer massive latency hits and ruinous token costs.
By making a simple shift from pattern 1 to pattern 2, which introduces a flat external vector store, you actually trigger a massive 90% reduction in tokens while simultaneously slashing latency down to just 1.44 seconds. That's exactly what the Mem0 Locomo benchmark revealed. Pattern 2 uses semantic similarity to grab only the top most relevant chunks. It's crazy fast. But because it's a flat namespace, a fact from yesterday and a fact from 6 months ago live in the exact same space. That can easily confuse an agent trying to follow a complex timeline.
Taking things a step further, pattern 3 actually mirrors operating system memory. It allows the agent itself to actively route data to hot, warm, or cold storage, which is exactly how you keep your cloud bill from looking like a phone number. In this model, the agent isn't just passively receiving context. It's actively issuing function calls to manage its own memory. It decides what to keep in its immediate working memory, what needs to be summarized into warm storage, and what gets archived into long-term cold storage. But what if you need temporal validity, like needing to know who owned a specific database table before an audit took place? Well, pattern 4 introduces a knowledge graph to handle exactly those kinds of complex relational queries. Vectors are awesome for finding things that are topically similar, but they are absolutely terrible at multi-hop reasoning. A knowledge graph explicitly maps out how entities relate to each other over time, which stops your agent from making critical decisions based on stale or superseded facts. Finally, we hit pattern 5. This is a massive paradigm shift from individual agent memory to true organizational memory, linking your agents directly to a certified, fully governed semantic layer. This is where Atlan's architecture really shines. Instead of an agent relying on some unstructured, ungoverned memory bank, it connects directly into your organization's existing data catalog. It accesses canonical metric definitions, live entity relationships, and strict access policies. It's the difference between an agent wildly guessing what revenue means and an agent knowing exactly how your business mathematically defines it. And let me tell you, this architecture pays off big time. Implementing this metadata layer results in a 3x accuracy improvement for complex tasks like text-to-SQL generation. When your agent has a live, governed semantic layer to draw from, rather than just raw, bare database schemas, the results are exponentially more reliable. Plus, it completely prevents the absolute compliance nightmares that inevitably happen when agents start hallucinating business logic.
Section 4. Avoiding token bankruptcy. So building these advanced architectures is absolutely vital, but we really need to talk about keeping your development teams out of token bankruptcy. Without proper memory tiering, a single 100-step task running with a 50,000 token context window, that is going to cost you $12.50 per run. That is completely unsustainable at scale. If you're paying for every single token on every single loop of an agentic workflow, your application will just hemorrhage money the exact moment you open it up to thousands of real users.
You can drastically reduce those hot-tier token counts by continuously summarizing older messages and setting up automatic decay for facts the agent just doesn't need anymore. For example, if a user asked about the weather in Toronto 50 conversations ago, your agent absolutely shouldn't be paying to keep that trivia in its working context window. By aggressively decaying low-importance facts, you keep your context incredibly lean and cost-effective.
Section 5. Checkpoints and state recovery.
The final piece of this maturity model is crash recovery. Think about this. If an agent fails at step 14 of a 20-step process and it doesn't have a save state, you're starting entirely from scratch. To fix this, you have to build a durable resumption loop using idempotent checkpoints. That way, a crash simply reloads the last successful state. Before each step, the agent's full state is serialized. Step succeeds, the checkpoint is updated. Crash happens, just reload. And crucially, this has to be idempotent. You need strict deduplication keys so that if your agent crashes right after sending an email to a client, reloading the checkpoint doesn't cause it to send that exact same email a second time.
Frameworks like LangGraph are actively leveraging tools like Redis to physically store these checkpoints and conversation caches. That's what actually prevents those duplicate API calls when a system resumes. As the open source community has noted, deploying this the right way requires specific modules, like Redis JSON to manipulate the state data, and Redis Search to index it. It gives developers incredibly fast, highly persistent storage for those essential mid-task saves.
Ultimately, the big takeaway from this explainer is that memory can no longer be this bolted-on afterthought feature. It has to be the foundational architecture of your entire AI enterprise. If you want agents that actually survive in the wild in production, they need to remember what matters, seamlessly forget what doesn't, recover from failures instantly, and respect the governed rules of your business. So, looking at your own systems right now, are you just crossing your fingers and hoping the context window is big enough, or are you actually engineering a memory architecture?